All right. There's no smooth way to do that. I got to click like four things, and they're counterintuitive, and I always almost end the broadcast every time I run through this checklist of things that I have to do. So if at some point I end the broadcast, don't be surprised. I will try
We
to.
will all understand.
I will
I,
start
I
doing it.
have actually clicked that
Have
button.
you? Yeah, because it's
Yes.
like you're seeing like you want to turn off the mute, but then the
Yeah, yeah.
rebroadcast
It's
button is
all
right
the
there.
things. Yeah.
Yeah. So how you doing? Welcome back to
Thank you.
North America. How was
It's
Poland?
Warsaw is a really amazing city, and it's fall right now, so all the leaves are yellows and oranges. And the city behaved in a great way for motivating us to go to the conference because during the days of the conference, the weather was rainy, foggy, awful. And then the day that the conference ended, it was suddenly glorious. So that was a great way to motivate us to go when we sometimes wanted to sleep and explore, and then to explore on the days that we were supposed to explore.
We're completely socked in here. It is like
Oh,
thick fog. Airplanes aren't flying. It's just
oh
terrible.
man.
Yeah, yeah. But and so it's just cold and clammy. But I got a chance to
Yeah,
try caving for the first time. So we've got some caves here on Vancouver Island. There's a ton of caves
yeah.
actually. There's some of the longest caves in the world are here on the island, and they're still
Really?
getting explored. Yeah, like 10-kilometer long caves. But the one of the best ones that's been explored is the Horn Lake Caves, and I went caving for the first time. And I was expecting you just like look around and there's big,
No.
you know, big open cave. You're like, yep, that's a cave. But no, it's like you're crawling on your belly through these tiny little chimneys, and you're climbing down rock faces, and yeah, it's a pretty constricting thing. So if you don't like
Yeah.
enclosed spaces, you would not enjoy this. And you're wet, it's raining, water's coming down all over you. So yeah, no, it's
I do not like caving. I've done some of the narrower parts of Mammoth Cave, where the big part is those huge, glorious caverns with stalactites and stalagmites and ponds and all that sort of stuff. But some of the other parts, it's like, okay, rotate shoulders 90 degrees relative to hips, squirrel through, and then rotate, and it's like doing yoga with spiky rocks.
yeah.
And I no, not
And
for
my
me.
yeah, my daughter had a real advantage because she's much smaller than me, so she was
Yes.
slipping through these things, and I'm like trying to
Yeah, the
squeeze through the
closest to
cracks.
caving I get is the City Museum in St. Louis. So that's
So we're going to record an episode of Astronomy Cast, and today it's going to be episode 318, Escape Velocity. So if you've never seen such a thing before, we will take about 30 minutes to record the actual episode, and then when we're finished, we'll stick around for a few minutes, and Pamela will be glad to answer any questions you have, including questions about space and astronomy. Uh,
preferably questions about space and astronomy.
a few biology questions, whatever, whatever you want. We still have yet to fully plumb the limits of Pamela's massive intellect. So I defy you to ask her a question she can't answer or that Googling won't answer. Um, yeah, and so there's a few places you can ask your questions. So one place is on the event page on Astronomy Cast. So if you're watching this over on Google Plus on the event page where it's embedded in there, you can ask a question there. The other place is on YouTube. So if you're really watching this anywhere else on the whole internet, and honestly, people can embed this everywhere. We have no idea where it is. You might be watching this on Universe Today right now. Just click on the bottom right, watch on YouTube, and then go and watch it on YouTube. And then that's going to be all the comments there, and I'll be tracking those comments as well. Feel free to post ideas while we're recording the show, and I'll try and incorporate them into the show. Otherwise, just ask some questions that you might have, and we'll stick around afterwards and answer some questions. So upon that note, how are you doing, Pamela? You ready to go?
I'm jet lagged as all jet lag can be, but I'm ready to record.
All right. Well, then I promise to only ask you the toughest questions. Um, okay. I'm ready to press record.
Okay. I am pressing record.
And?
It's thinking.
Yeah?
And it's not in mono.
Should we start again?
Yes. I was doing so well for so long.
It's
Okay.
got to be some default that you just press and it just
I,
remembers.
I wish, but no, there isn't.
No.
Okay, pressing record again. And it's working.
Mine
It's
is
working
also
much
working.
happier.
Okay.
Okay.
Let me grab this. All right, here we go. Astronomy Cast, episode 318, Escape Velocity. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. Now, everybody loves your voice. I can't
People
argue
love
with
your
that.
voice too.
Well, so the thing is that I was like talking to someone on the phone about scheduling some room for an event, and
Right.
someone's like, "Are you a professional speaker or something?" I'm like, "Well,
Yes,
no."
yes, you
Well, I
are.
didn't want to explain, so I'm like, "No, no." She's like, "Well, you've got a really nice voice." So I don't know what it is. Maybe I've been taking notes from you, Pamela, but it's like the first time anyone's like, "Oh, you should like be in broadcast." I'm like, "Oh, okay, awesome."
But you are in broadcast.
I know, but I didn't want to explain. Like, I do a podcast about astronomy. Like, what? So anyway, I thought that was great because everyone's like, "Oh, I love Pamela's voice. She should." Yeah. So that was my first time. I know you've gotten zillions of them, but there you go. So you're back from Poland.
I am. I am suffering an 8-hour time change. But yeah, I'm back. It was a great conference, met up with people from all over the globe that are working to use all means possible to engage their local populations and global populations in learning and doing astronomy. So that was really fantastic, and there's going to be blog posts coming. I was live streaming everything using Google Hangouts on air, so I couldn't type effectively because if you type, you silence your Hangout. So there's a lot of catching up to be done.
But the bottom line is that if you're interested in any way about communicating astronomy to the public, which of course we sure are, check out all of the work that Pamela's been doing with this latest conference. And mountains of information came out, lots of meetings,
Yeah.
lots of video you guys recorded, lots of panels, documents. It's going to be a gold mine for
Yes.
communicating astronomy to the public.
And we're working on putting together a circle of astronomy communicators. So drop me a note on Google Plus if you want to be part of the circle.
That sounds great. And speaking of Google Plus, of course, we record Astronomy Cast live every Monday at 12 Pacific, 3 Eastern. And so right now we are recording this as a live Google Plus Hangout. So a few ways you can find that. You can find that just on the Astronomy Cast page on Google Plus. And we'll post an event every week, and you can join it there. And then, of course, we'll post the follow-up video back on Astrosphere, so you can catch up. All right, well, let's get rolling.
Okay.
So sometimes you've just got to get away from it all, from your planet, your solar system, and your galaxy. So if you're looking to escape, you'll need to know just what velocity it'll take to break the surly bonds of gravity and punch the sky. I hope people know what reference that is. It's from The Simpsons, which is it's a little different in The Simpsons. But anyway, so today we're going to talk about escape velocity, and I think the great thing is to kind of go back to, what was it, Newton? Like who really figured this concept out in the first place?
It was Newton who started to put together the concepts of gravitational potential energy, kinetic energy, and the fact that our moon is literally just falling around and around and around the planet Earth. And so Kepler started it all when he realized that orbits aren't perfect circles, they're ellipses. And then thanks to the development of calculus, which wasn't just Newton, we know Leibowitz and others were involved as well, they were able to take it from orbits or ellipses to orbits or conic sections, where you can have parabolas, hyperbolas, and then, of course, our beloved ellipse. And each of these different shapes corresponds to a different way that energy is involved in describing the motion.
And so what was that big, I mean, we always think about that apple idea about gravity and stuff. What was this, with Newton's watching an apple fall, and then he thought, oh, I see, everything's falling towards the Earth, or that the moon's the same. So what was this insight that he had, and how that led to this concept of escape velocity?
Well, it boils down to three different things coming together at once. First, you have the idea that was put forth initially in part by Galileo, that an object in motion tends to stay in motion. It was Galileo that worked to figure out friction and figure out how inclined planes worked and gravitational potential energy becoming kinetic energy. Those words weren't fully developed with Galileo. It took a while to develop everything out. And then you had Newton coming up with the idea that force is a way of describing mass times acceleration. So now you have forces acting on objects in order to accelerate them. So you have an object, the moon, that is traveling with a velocity that would like to be a straight line. So since the moon isn't traveling in a straight line, since it does continue to go in circles around our planet, which isn't going in circles around the sun, so really the moon's spiraling, that means there must be a force acting on it. And in this case, the force of gravity. And, well, if it's falling but going in a straight line, how is it that it's not hitting the Earth? And it's that combination of, well, it's moving along the orbit and falling, and the rate of falling is such that it just misses the surface over and over and over again.
Right, and he had this analogy that if you like shot a bullet or from a cannon,
Cannonball.
a cannonball, yeah, yeah. So how did that work out?
Well, the idea is that if you throw a ball or very weakly fire a cannonball, it's going to try and move forward with set velocity. But it's going to end up curving down to the surface of the planet Earth. And if you're working on calculating these equations for a small enough region that you can assume the Earth is flat for the region in the calculation, you can use constant forward velocity to figure out how far it goes across the surface of the planet, and then use the acceleration of gravity to figure out how long it takes it to fall from whatever the height of the cannon is above the ground. Work those two equations out, and you can figure out where your cannonball is going to land. Well, if you fire the cannonball harder, it's going to move faster before it finally hits the ground. If you fire it fast enough, the Earth's surface starts to curve away. So now you have to figure out, well, the Earth's surface is curving away. Now where's it going to end up? And you work the equations hard enough, and you figure out if you fire that cannonball with enough velocity, enough initial velocity, it's going to sail all the way around the planet and hit the cannon in the butt. And if you fire it even harder, it's actually going to fly away from the Earth altogether.
And that little bit farther is that escape velocity.
Exactly.
Right.
And at a certain level, it all comes down to, well, the Earth is trying its gravitational best to pull that cannon down to its surface. But if the kinetic energy is great enough, the kinetic energy, the motion of the cannonball, can act such that it overcomes the gravitational potential energy trying to pull it down.
Well, and so I think you've described it as this idea of this cannonball being shot sideways around the Earth, and the ball goes all the way around and comes back and
Yes.
hits the cannon, or just misses, grazes the top of the cannon, just keeps
Yes.
going. And obviously, air resistance is going to pull it in, and so on and so forth. But what if you took your cannon and you shot it just straight up?
In this case, on small scales, it goes up and it comes back down and hits the launch pad. If you launch it a little bit further, well, the rotation of the Earth at the surface is going to be such that the two are sort of moving together. You add in air resistance and things, it doesn't end up landing directly on the launch pad anymore.
But let's imagine that it does. I mean, just, in a sort of your cannon's on a vacuum and the planet's not rotating. I mean, we've talked about the idea of you shooting it into this circular orbit, but I guess if you shot it straight up, how hard would you have to be able to shoot the cannonball? Like, is it possible that you could make it never come back, or will it always come back?
Yes. In fact, you just have to fling it at 11.2 kilometers per second. And this is the velocity at the surface of the Earth, assuming sea level and all that sort of stuff, at which the kinetic energy, the 1/2 mv squared energy of the rocket at launch, is able to overcome the gravitational potential energy at the surface of the planet. Now, if you launch from higher up, you can go slower, and this actually means that you don't have to maintain that huge velocity the entire time you're trying to escape.
But isn't the like the Earth, I mean, the gravitational field of the Earth extends pretty much across the entire universe, right? Just
Right.
very small amounts is the further away you get. So it's always going to be pulling on the cannonball. It's just that it won't be pulling on the cannonball hard enough to pull it back in.
Exactly. And the truth is that if you have zero velocity and you're set down in the gravitational field of our solar system, so let's say zero velocity relative to the sun, you need something to be relative to if you're measuring velocity. So if you use the sun as point zero zero in our new coordinate system, 000, it's three-dimensional, and you have no velocity relative to the sun, as a planet sweeps by, its gravity is going to give you motion. So will the sun. And eventually you're going to end up falling into something. It's only when you have some sort of a kinetic energy that you're able to escape all of these different gravitational pulls.
Right. And so what has an effect on the, again, assuming this planet in a vacuum, what has an effect on the escape velocity? You mentioned, was it 11.2
Kilometers per second.
kilometers per second? That's really fast, right? I don't think people realize just how fast you have to be going to get off the planet.
Well, it could be much worse. So our sun, for instance, I'm looking at a table here. Our sun has 617.5 kilometers per second. So I'm not sure I've gone 600 kilometers per hour except in airplanes. And you have to be going the rate that an airplane going fairly fast goes in 1 hour, except you have to go that distance per second to get off the surface of the sun.
Wow.
Yeah.
Right. And so what has an effect? I mean, obviously, like the mass
Right.
is the
But
big
that's
part.
only half of it. And it's actually not the bigger half of it because your distance from the center of the mass is actually a factor that gets squared. So when you look at the force of gravity on the surface gravity that you're being subjected to, that surface gravity is the gravitational constant, which is what puts metric into the universe's units, times the mass of yourself, times the mass of the object you're on, over the radius between you and the center squared. So that's the force that you're experiencing. Now, the potential energy, it luckily doesn't have that radius squared anymore, but it's still there. In this case, the gravitational potential energy is the force multiplied by your distance. So you have GMM, so your mass, Earth's mass, gravitational constant, all over a single distance between you and the center of mass. So if we made the Earth significantly smaller, the gravitational potential energy that we'd have to escape from at the surface would get much bigger. So if we kept the same mass of the Earth and we cut the radius in half, the potential energy would double. You with me?
I am. Yep.
Okay. So then our kinetic energy, that's the energy of motion. So when I jump up, at the moment my feet leave the ground, I have a velocity. Now that velocity decreases the higher up I get until it hits zero and I reverse direction and go back down towards the surface of the Earth. The way that my velocity varies is this combination of kinetic energy going down, maximizing gravitational potential energy going down as kinetic energy goes back up as I get closer to the surface as I fall.
Right.
So that kinetic energy is 1/2 because 1/2 is reasons, take university physics.
Reasons. My favorite explanation.
And times the mass times the velocity squared. So there's a mass on both sides of these equations. So the reality is my mass has nothing to do with the escape velocity. I can cancel that out on both sides. So what I'm left with is velocity squared is proportional to the mass of the object over the radius of the object when it comes to trying to get off of a planet. And the faster you go, the easier it is to escape.
And so how much? So if you cut the radius of the planet in half, essentially
Right.
make it twice as dense, four times as dense. I'm just trying to think how much more dense that makes it. Then what impact does it have on the escape velocity? Is it
So,
double or
so
does it go up by the
no,
square?
it's a square issue. So it's velocity squared. So now it's the square root. So it would be you'd have to go the square root of 2 faster.
Right. I see. Okay. Um, yeah. So that has, as you said, that is
This is
that
so much easier to teach with a chalkboard,
with
I
the
just have
chalkboard.
to
I know.
say.
I know. There's times, with the video, maybe we should let you bring up a whiteboard and actually start doing math. But no, no, this is a good experiment. Right. Okay. So then let's look at some other objects in the solar system. You talked about the
Right.
sun, and you've got a handy table in front of you. So what are
I
some other
I
objects
do.
that, what's the escape velocity from some other objects in the solar system?
So Ganymede, a happy little moon, it's 2.7 kilometers per second. Pluto is just 1.2 kilometers per second, so that's not that bad in the grand scheme of things. Mercury, 4.3. Moon is just 2.4 kilometers per second, so it's actually fairly easy to get things off the moon in the grand scheme of things. Uh, Jupiter's a bear. Jupiter's 59.5 kilometers per second.
Right.
And so it's tricky. Now, one of my favorite things is the gravitational acceleration at the surface of Saturn is very similar to what it is at the surface of the planet Earth. Um, but because the gravitational acceleration that you deal with is proportional to the radius squared, um, the potential energy you need to escape isn't the same on the two objects. So on Saturn, you have to go a whole lot faster. You have to go 35.6 kilometers per second to escape, unlike Earth's 11.2.
So let's imagine some futuristic rocket ship that is going to travel outside of the Milky Way, for example.
Okay.
So we're going to need to first escape from the Earth. So
Right.
we're going to need to go that 11.2 kilometers per second to get off the Earth.
Yes.
Then we're going to need to escape the sun.
Yes.
Not from the
So
surface, but from far away.
right, right. So that one isn't too big a deal. Um, I don't have that number in front of me, of course.
No, no,
You
but
always
well, you know what? I highly
so
recommend. I don't know if you played it yet, but I highly recommend the Kerbal Space Program.
yeah, yeah, no, I know Kerbal is awesome.
Yeah, this stuff all now utterly makes sense to me, and right, because I'm like, I know how
Right.
big to rocket I got to build to be able to
Yeah,
make it be on a solar escape velocity.
right. So I just don't know what the sun's escape velocity is at like the distance of Voyager. I know from the table I'm looking at that at the distance of Neptune, you have to be going 7.7 kilometers per second to escape the galaxy. Not galaxy, the solar system.
Right.
And then to escape the galaxy from our solar system's distance, it's, well, more than 525 kilometers per second. And I'm being guilty of using Wikipedia for all of these numbers for people who want a citation.
Right.
Um, so you have to get going pretty darn fast if you want to escape our galaxy. So you're looking at that's the number that you care about most is the biggest number. So you need to be going greater than 525 kilometers per second to escape our solar system.
And the amazing thing is that we've talked about this in the past that there are stars
Yeah,
which are on this escape velocity that have gone
exactly.
through interactions or gotten exploded by supernovae or something, and they're out of here.
They got a good kick. They were given a kinetic energy that can overcome that gravitational potential energy.
As always, I like to go to extremes. So I'd like to go for the like really low escape velocity.
Okay.
So what are some places in the solar system where it's very low, and what could you do?
Well, some of the asteroids are just barely able to hold on to even smaller asteroids. And so in these cases, you have these very gently arcing small moons around giant building, admittedly sized asteroids. So that's not a whole lot of gravitational potential energy, um, but they're still able to hold on to these things. And if an asteroid gets small enough, um, then were you able to very carefully get yourself onto the top, you could spring yourself off and fly away. And that's just kind of cool to think about asteroid hopping, literally asteroid hopping, except the
Literally,
asteroids are very far apart, so you
right.
can't really bounce from one to another or even see one from another.
Right, but the bottom line is that if you're not careful and you're some asteroid miner on the wrong sized asteroid with a low enough density, you could very well jump and just not come back.
Here, I think we're talking about asteroids that are so small that mining them's kind of a pointless endeavor. So we're good.
Right. Dismantling them because they're just a little rubble pile.
Right, right.
Yeah. Yeah, but that's kind of scary. Like, it makes me think of Gravity, the movie where you
Which I still have not seen.
oh, go see it.
I was out of the
I know, I
country.
know, I know, and they don't have that movie in that other country. Anyway, so right, so that's really light. I mean, you can imagine these situations, and there's these, I've seen some of the mission plans for some of these asteroids. It is essentially that you are weightless. I mean, you're not walking across
Yeah.
the surface. You are, there are
Trying not to fly off of
yeah,
this.
you're bolting on a ladder type system that you're going to crawl around the outside of this asteroid on and bolt yourself in like a rock climber to try and stay connected.
Right.
Okay, well then let's go the other way. So let's go to extremes. Like what about white dwarfs?
Right. So I was just looking that up because I figured that was going to be your next question. And of course, it gives me an answer in miles per hour when I look it up. So it's over 2 million miles per hour. Let me convert that to kilometers. And we both begin to type.
Yeah, sorry, Preston.
So um, it's 4.6 million kilometers per second to escape the surface of a white dwarf star.
Right.
So you're not really going to do it.
No, there is no getting away from a white dwarf star. That's crazy. But that's nothing.
But no, does that make sense though? That's faster than the speed of light, isn't it?
I've got 320. You want to do that again? Because I've got 3.2 million kilometers per hour.
Hold on. The place where I looked it up, I think, must have been wrong
Did you
because
say it was 2 million miles per hour or 200?
the sorry crowd, this is something I didn't anticipate being asked. So miles per hour, not miles per second. Okay. Now it makes sense. Yes, that's not faster than the speed of light. Yeah, so
Do you want to start that
2.8.
whole sort of thing again?
Yeah, let me do the unit conversion.
I said, what about a white dwarf?
I know, I know. Let me uh, convert back to kilometers. Okay, I got it. Sorry, Preston. First, going to apologize. So white dwarfs are kind of obscenely dense. A tablespoon of them is more than several elephants worth of mass. And to escape one of these, you're looking at having to go roughly 4.5 million kilometers per hour. So it's a lot.
Thousands of kilometers per second. Yeah.
Yeah, exactly. Not the speed of light, but really darn fast.
No, but we've talked about it in another show, an even more exotic object, which is a neutron star, right? This is the situation where the gravity has pulled the electrons and the protons together, and all you got is neutrons.
And here you're just adding a couple of zeros. So this is now 100 times faster. So you're looking at 450 million kilometers per hour.
I just worked on an article about this. It's 100,000 kilometers per second. So it's a third the speed of light?
Yeah, so these are objects so dense that even protons and electrons can't stay apart.
Right. And only light can escape from them.
Yes.
And it does. I mean, you get pulsars. So you got a situation where light is escaping from them. So now the final solution here for the most extreme densest object, highest escape velocity is a black hole, right?
Yes. And a black hole, by definition, the lowest possible escape velocity is the speed of light. And we don't quite know where the surface of a black hole is. So we generally define them as having an escape horizon. And the escape horizon is that point at which you're so far away from the black hole that and so near at the same time. So it's this balancing point where if you got any closer, you'd have to go faster than the speed of light to escape. But if you went any further away, you could escape going slightly under the speed of light. But at that Schwarzschild radius, you have to go the speed of light, which you can't, so you can't escape.
Right, and I guess the size of that Schwarzschild radius, that event horizon, changes depending on the mass of the black hole. You get a supermassive
Exactly.
black hole, and it's the size of a solar system.
Right, and you get a microscopic black hole, and it can slide down between molecules.
Wow. Yeah, it's a funny thing about black holes that really it's all just about compressing the mass down. You could have
Exactly. How
a,
close to that center of mass can you get?
can you get, and then it turns into a black hole.
Right, so you can have extraordinarily small black holes that don't even have all that much mass, but the amount of mass they have is in such a tiny, tiny, tiny space that you could get close enough to the surface that you need to go the speed of light to get away.
And so then, I mean, we don't know what's inside of a black hole,
No,
right? So we
no.
don't know if there is a place inside that is infinitely small, like who knows what the actual escape velocity of a black hole might be.
Um, well, we don't know if they have a surface, so
Right.
that starts to make the question silly. Um, if they do have a surface, it's quite feasible that the escape velocity can be thousands of times the speed of light for some of these objects, perhaps even more. We don't know how small things compress down. We don't know what state of matter they achieve. There's a lot we don't know. And so just as Newton came along and took Kepler's ideas and made them science, Einstein came along and modified Newton's ideas to work under relativistic extremes. And now we need that next person who comes along and grows the theory so that we start to understand what's happening within the escape horizon.
Could a black hole get smaller than the Planck length?
We don't know.
Don't know. So imagine like a supermassive black hole, like the most massive supermassive black hole in the universe, that much mass, but the size of a Planck length. What would the escape velocity be? Someone do the
I'm not going to
math.
calculate that.
Someone do the math. That'd be a horrible number. Yeah. Yeah, that would be amazing. Cool. Well, thank you very much, Pamela.
It's my pleasure. Thank you.
All right, I've stopped the recording.
Yep, saving.
Exporting.
Sorry, everyone, for being very jet lagged.
No, you were great.
I also became unable to differentiate between miles per hour and miles per second, which hopefully was amusing to others.
Ah, they're the same. Sorry, I'm just going to upload and then so we're safe. We're safe, but for how long? Right. I'm good. I'm uploading now. Okay, let me see if we've
Okay.
got some questions piled up here. Nope, no questions. Okay, good night, everybody. No, got some stuff here. All right. Guido Bibra says, no excuse for Pamela. Gravity has been in Polish cinema since October 11th and in Germany since the 3rd.
I
You were busy.
did
You
not
were
go
busy.
see it.
You were
Yes.
doing astronomy communicating, going and seeing what is probably the finest movie this year and easily one of the best space depictions of space travel ever done.
It will happen. It just hasn't happened yet.
Do you have like an IMAX theater nearby?
No,
Okay. Do you have a 3D theater nearby?
maybe.
Okay. See it in 3D if you can. It's terrific. Sylvan Westby reminds everyone to play Kerbal Space Program. I agree. See the Kerbal Space Program. Play that game. It is awesome. It's like $20 on Steam, and it's just fantastic. And they did a new update this week, I think.
Oh,
So
cool.
yeah, a bunch of people are saying that my audio is really low. Is it maybe because I mean you don't know because you only hear my audio and compared to anybody else
Right.
in this Hangout. So I hope our audio is the same.
It will get adjusted yeah, our green liney thingies are very, very different.
Um, okay, so Andrew Planet asks, does escape velocity differ relative to the distance from the object gravitationally attracting?
Yes. Yes.
Yes.
So the numbers that we stated were all from the surface.
Yes. Okay. Um, let's see. So Michael Jobin asks, uh, what would happen if the Earth was hollow, say maybe 10 kilometers? How would walking on the surface be different?
If it had the same mass and it was just like squished into a shell, walking on it wouldn't change at all, but the planet's moment of inertia would change. So how it behaved if it got struck by a rock would change.
Right. Okay. Okay. And so really it just comes down to the density
Yeah.
of the like the
The
total mass and the
average.
total size of the whole thing, the average
Yeah.
across the entire structure.
Yes.
So it would be
Integrated is the correct way to look at it.
right. And so it would be indistinguishable if it was, say, a thin shell that had the mass of a white dwarf or the density of a white dwarf or a planet like we have. As long as it's the same size and the same amount of mass in that same size.
Right.
That's cool. Um, yeah, Rob Holland says, yeah, the original reference to that is from the poem High Flight. Oh, I have slipped the surly bonds of earth, put out my hand and touched the face of God. Yeah, and then The Simpsons totally modified it. It's great.
I well, and my poor brain is broken in such a way that the second you say the word surly, I go to Surly Ramix and Amy Roth. Go buy her stuff; it's awesome. And so I'm like, you're slipping jewelry to escape the bonds of Earth. But okay,
Noel Rupenthal says you can do science in the Kerbal Space Program now, so that's cool.
cool.
Yeah. Um, let's see. So Steve Heistland says there are impulse initial velocities, but what about having a thrust engine and a boatload of energy to power it? So I think that's we're talking about like one kick, boom,
Yeah.
you get you get all of your velocity in one big kick, and then you've got to drift for the rest of your journey.
And the reality is that they do fire engines constantly, so you don't have to achieve the 11.2 kilometers per second.
Right, because as you're getting further away, the the speed, the escape velocity of where you are goes down.
Right.
Right. Okay. Michael Jobin asks, I wonder if light would behave differently in a neutron star.
It gets bent a lot. Gets
So
redshifted.
it gets redshifted, distorted around the size. I mean, would you have some relativistic effects at that
Yeah,
level?
yeah. No, that's where you start getting gravitational redshifting and stuff.
Yeah, okay. So yeah, absolutely, light would get all wacky, and we see that. I mean, the great thing
Yeah.
about these neutron stars is that we can see them, and we can see the light pouring off them in these extreme environments.
Well, and even more cool when they're in binary systems, you can start to see the energy lost to gravitational waves.
Einstein, once again, correct.
Yes.
Um, so, and Noel Rippenthal also asks, so are black holes not compacted to a zero-dimensional point and have no real surface?
Don't
So
know.
we don't know, yeah. Maybe they have a surface, and maybe they are a singularity of infinitely small size and density. Okay. We literally do not know. I love that. I love that we don't know. Let's see if this got any more questions. Ronnie Pearson asks, do we have dark matter in the center of our Earth?
We have dark matter everywhere.
So yes. In fact, we have dark matter in us right now. Dark matter here in the room with us.
Yeah.
Just not much.
It's a factor. Well, it outweighs the regular matter. It's just
you just blew my mind. Okay, hold on a second. Now, dark matter outweighs regular matter across the entire universe,
Yeah.
but does it outweigh regular matter on a local scale as well?
Not necessarily, but it could. It would. I haven't actually done the calculations. I'm just doing things off the cuff, so I might have just made a mistake there. But
Right, but I mean, like for example, like the Milky Way is
yeah,
embedded
we
within a
are
dark.
significant. We are significant overdensity. So no, there's not more in the room with you, but there is a lot in the room with you.
Wow, that's cool. So right, but when you have like planets and things like that, then it's way in the case of matter and not in
Yeah,
dark matter. Because
right.
you get the situation where dark matter just
Yeah,
it
you have
doesn't
to smooth it
accrete.
by volume, and we are such an overdensity that yeah, I forgot how big an overdensity we jet lagged. Jet lagged.
So
Forgive
so
me.
yes, we have dark matter in the room with us. As it relates to the amount of matter, like air is, we have way more density of air than dark matter, but there
Yeah.
probably are the occasional dark matter particle around nearby.
They're just a bear to detect, and we haven't successfully, in a statistically, yes, we're certain kind of way, done it yet.
Right. Okay. Um, I think that's all I've got.
Sounds
Anyone
good.
else got a question?
Otherwise, I'm going to go make more coffee.
Me too. Okay, cool. All right, well, then I'm going to wrap this up. So thanks everyone for watching. Thanks as always, Pamela, for recording with me, and thanks for returning back to the United States, safe and sound.
Yes, it's good to be home.
Yeah. You got anything else happening in the far
In
future?
November, I'm going to be in Indonesia. There will be a public talk in Jakarta. I will announce the date when it's set. And then I'm going to Bandung for the Southeast Asian Young Astronomers Conference.
I will be in Los Angeles in 2 weeks. 3 weeks? Yeah, but I'll be able to record while I do it. So
Okay,
I'll be
cool.
recording from an interesting place. So I will keep you posted.
Sounds good.
All right, cool. Well, thanks everyone for watching. Thanks again, Pamela, for joining us, and we will see you all next week.
Sounds good. See you later. Suddenly glorious. So that was a great way to motivate us to go when we sometimes wanted to sleep and explore, and then to explore on the days that we were supposed to explore.
We're completely socked in here. It is like
Oh,
thick fog. Airplanes aren't flying. It's just
oh
terrible.
man.
Yeah, yeah. But and so it's just cold and clammy. But I got a chance to
Yeah,
try caving for the first time. So we've got some caves here on Vancouver Island. There's a ton of caves
yeah.
actually. There's some of the longest caves in the world are here on the island, and they're still
Really?
getting explored. Yeah, like 10-kilometer long caves. But the one of the best ones that's been explored is the Horn Lake Caves, and I went caving for the first time. And I was expecting you just like look around and this big,
No.
you know, big open cave. You're like, yep, that's a cave. But no, it's like you're crawling on your belly through these tiny little chimneys, and you're climbing down rock faces, and yeah, it's a pretty constricting thing. So if you don't like
Yeah.
enclosed spaces, you would not enjoy this. And you're wet, it's raining, water's coming down all over you. So yeah, while we're recording the show, and I'll try and incorporate them into the show. Otherwise, just ask some questions that you might have, and we'll stick around afterwards and answer some questions. So upon that note, how are you doing, Pamela? You ready to go?
I'm jet lagged as all jet lag can be, but I'm ready to record.
All right. Well, then I promise to only ask you the toughest questions. Um, okay. I'm ready to press record.
Okay. I am pressing record.
And
It's thinking.
yeah,
And it's not in mono.
should we start again?
Yes. I was doing so well for so long.
It's
Okay.
got to be some default that you just press and it just
I
remembers.
I wish, but no, there isn't.
No,
Okay, pressing record again. And it's working.
mine
It's
is
working
also
much
working.
happier.
Okay.
Okay.
Let me grab this. Yeah, no, it's
I do not like caving. I've done some of the narrower parts of Mammoth Cave, where the big part is those huge, glorious caverns with stalactites and stalagmites and ponds and all that sort of stuff. But some of the other parts, it's like, okay, rotate shoulders 90 degrees relative to hips, squirrel through, and then rotate, and it's like doing yoga with spiky rocks.
yeah.
And I no. Not
And
for
my
me.
yeah, and my daughter had a real advantage because she's much smaller than me, so she was
Yes.
slipping through these things, and I'm like trying to
Yeah, the
squeeze through the
closest to
cracks.
caving I get is the City Museum in St. Louis. So that's
So we're going to record an episode of Astronomy Cast, and today it's going to be episode 318, Escape Velocity. So if you've never seen such a thing before, we will take about 30 minutes to record the actual episode, and then when we're finished, we'll stick around for a few minutes, and Pamela will be glad to answer any questions you have, including questions about space and astronomy.
preferably questions about space and astronomy.
A few biology questions, whatever, whatever you want. We still have yet to fully plumb the limits of Pamela's massive intellect. So I defy you to ask her questions she can't answer or that Googling won't answer. Um, yeah, and so there's a few places you can ask your questions. So one place is on the event page on Astronomy Cast. So if you're watching this over on Google Plus on the event page where it's embedded in there, you can ask a question there. The other place is on YouTube. So if you're really watching this anywhere else on the whole internet, and honestly, people can embed this everywhere. We have no idea where it is. You might be watching this on Universe Today right now. Just click on the bottom right, watch on YouTube, and then go and watch it on YouTube. And then that's going to be all the comments there, and I'll be tracking those comments as well. Feel free to post ideas. All right. There's no smooth way to do that. I got to click like 4 things, and they're counterintuitive, and I always almost end the broadcast every time I run through this checklist of things that I have to do. So if at some point I end the broadcast, don't be surprised. I will try
We
to.
will all understand.
I will
I
start
I
doing that.
have actually clicked that
Have
button.
you? Yeah, because it's
Yes.
like you're seeing like you want to turn off the mute, but then the
Yeah, yeah,
rebroadcast
it's
button is
all
right
the
there.
things. Yeah.
Yeah. So how you doing? Welcome back to
Thank you.
North America. How was
It's
Poland?
Warsaw's a really amazing city, and it's fall right now, so all the leaves are yellows and oranges. And the city behaved in a great way for motivating us to go to the conference because during the days of the conference, the weather was rainy, foggy, awful. And then the day that the conference ended, it was